I'd like to thank the organizers for inviting me. Okay. So I want to introduce a certain particular sequence of operations on digraphs. First of all, so let me define some particular graphs first. So quiver is just a finite. Quiver is usually just a direct graph. It could be infinite or finite. But if I say cluster quiver, then I mean directed graph. I want to remove very short oriented cycles. There is a reason for this one. It comes from mathematical physics. It comes from string theory. These two cycles or shorter cycles do not contribute to supersymmetry, so we do not consider this. But anyway, this is my definition of a cluster quiver. But I'll just for brevity, I'll just say. This is a quiver. Okay. So, and I want to introduce an operation which transforms the quiver into a new quiver. So in mathematics, it is called the quiver mutation. But actually, this was invented by physicists. So originally in physics it was called the Seiberg duality, and this is Seiberg introduced this operation, and then in the context of string theory. So the idea is that if we have, so we can choose any vertex of a digraph, and then we can take a Seiberg duality at any vertex. Suppose that I take a vertex J, then if I apply a Seiberg duality, then it would become it's like this. So basically, I want to take a composite of these two arrows, and then make a single arrow from I to K. But to compensate these directions, the arrows that are incident to J will be reversed. So like this. And if this is a good duality, then the dual of dual should be the original. So I want to come back by applying Seiberg duality at J here. So, but if I apply Seiberg duality on this graph, then I will get something like this. Again, I want to, since there is a path passing through J, I want to draw a single arrow from K to I. This is an old arrow, and I draw a new arrow from K to I, and then I need to reverse these arrows. But since I want these to be the same, I will actually cancel two cycles. So that's why I don't allow these cycles of length less than or equal to 2. So just to cancel two cycles. Then I'll get a good notion of duality. Yeah.
So these diagrams, they represent the whole neighborhood, the in neighborhood and the out neighborhood.
That's right. I'm just loosely introduce Seiberg duality. Actually, I make a precise definition. Yeah. Yeah, actually, yeah, I have to consider all possible path passing through J. Yeah. Okay, so and then actually, the physicists have never precisely defined the cyborg duality. They just have had this concept, and then they didn't really use these notions. I'm not going to say much about this. Anyways, in string theories, they introduce cyborg duality because they want to study certain moduli space of quiver representations, and then so for each quiver, we can associate with a moduli of quiver representation over a given quiver. And in string theory, one of the biggest problems is to compute the Euler characteristic of this moduli space. And physicists observed that under cyborg duality, the space of this moduli space over this thing and this thing are the same. So they apply cyborg duality, keep applying cyborg duality until they get the simplest quiver, and then they study the simplest quivers. Anyway, that was history. And as I said, I need to make a more precise definition. When I say quiver, I mean actually cluster quiver. I can choose any vertex. Let's say any vertex. And apply the mutation, then this will result in a new quiver. I will denote by mu j of q. And I'll just make what I said here, make a precise what I said there, and then so. So as I did there, I will just look at every path passing through J, path of length 2 passing through J, and then create a new arrow from I to K, and then and reverse the arrows that are attached to J. And then finally, these step 1 and 2 will possibly might introduce cycles, 2 cycles, and then we just cancel 2 cycles one by one. Oriented cycles of length 2. So later on, I need this example, so I will draw this example here. Okay, so suppose I have a quiver with 4 vertices, like this. And if I mutate at 1, then it will become, there is no oriented path passing through 1, so we don't have to do step 1. Just to carry out the step 2, then we just reverse the arrows instantly we want. So we get this one. So this is easy. And of course, there are no oriented cycle, no 2 oriented cycles created. So there just step 2 is enough. And after that, we can also apply another mutation at any of the other vertices. So if I mutate at 2, oh, by the way, if I mutate at 1 again, then by the analogy of Seiberg duality, I will get back to what I had before, and then mutate at 1. Still, there is no oriented path passing through 2, so this is a very simple mutation. But anyway, the result is, if I look at just quiver, this subquiver with vertices 1 and 2, then 1 and 2 become the same, but just these orientations from 3 to 1, 4 to 1, to 4 to 2 were reversed. And actually, a more interesting example would be the following. Mutating at 1 seems to be most interesting because it contains 2 paths passing through 1. So away from 1 or other arrows are just fixed, and then I need to create new arrow from 2 to 4 and new arrow from 2 to 3, and then reverse the arrows instantly with 1. And there is a 2 cycle, so I cancel this one, and then I cancel this one. Yeah, that's it. Okay, so this is a quiver mutation, and then although this looks a little artificial, but it has many applications in almost every branch of mathematics and physics. If I have time, I will mention some applications in other branches besides from combinatorics. I mean, this precise mathematical definition was made in 2001 by Fomin and Zalewski. I mean, they independently introduced this notion, but later on they realized that this notion was already existing in physics. Since it appears in many areas, and so since 2000 there have been many papers, more than 1,200 papers. So, but since this is combinatorics conference, so I want to just introduce the combinatorial feature of this thing. Okay, so one mutation is already interesting, but I would like to take a sequence of mutations like this. So I want to mutate at every possible vortices and every possible directions, and I want to take every possible sequence of mutations. Sometimes I get, I mean, in most times I get infinitely many quivers, but sometimes if I'm lucky, I'll get just finitely many quivers. As I said, I want to take a sequence of mutations from the quiver Q, and I want to collect all possible quivers obtained that way. Class of quivers. Okay, so when I introduced this physics history, string theorists actually is using this notion to simplify quivers, but mathematically we need to make more precise about what is a simple quiver. So we need to consider all possible quivers, and then we need to identify which ones are simpler than the others. But sometimes it's not really easy to identify which quivers are simpler. In particular, if this mutation class is finite, then it's really hard to tell. I mean, if this is finite, then almost all quivers are fairly simple. So. Actually, this finite mutation class is completely classified. I'll just give a name for this particular class, mutation class. And then the classification is as follows. I mean, before 2008, there have been many people working on which ones are mutation finite type. There have been many progresses. Finally, they completed this picture. Okay, so there are three classes. First of all, the simple one is if there are few number of vertices, then we cannot do much. So there are just finitely many quivers. I mean, if you have just two vertices, then or even if you take a mutation, you just reverse arrows only. That's all. So there will be only two quivers in this class. The second class is the most interesting one, and actually it's dominating mutation finite type. When I say a surface is a Riemann surface, real dimension 2, it could have boundaries, it could have marked points. And then the third is unfortunately, there are badly behaved exceptional classes, but there are only 11 classes. So. I will just give names, but I will not draw quivers. It's something like this. Again, they have relatively fewer number of vertices, less than 10, maybe. And it took a number of years to find these two exceptional classes, and then another years to show that these are the only finite mutation class. E6, for example, E6 looks like just the underlying undirected graph is just a Dinkin graph E6. You can just give arbitrary orientations on that, and these E series are similarly. It looks like something like this, and X6, X7 are really exotic. X7 looks like. Like this. Although it looks complicated, there are only two quivers in this mutation class. So there is not much we can do in this mutation class. Okay, so I need to say why a quiver can come from triangulation. Okay, so if I have a surface, arbitrary surface, arbitrary genus, but for simplicity, let's just take let's just take a look at partial triangulation. I might have bigger surfaces and other triangulars, but if I look at just locally, then there will be two triangles that are adjacent to each other, and then let's label the edges. Let's say 1, 2, 3, 4, 5. And these edges correspond to vertices of a quiver. And the relation between edges will be an arrow here. So I can choose either counterclockwise or clockwise direction, but counterclockwise direction seems to be conventional. So let's take this one. So then the corresponding quiver looks like this. 4, 3, 3, 2, 1. 1, 2, 2, 2, 2, 5, 5, 2, 1. And although this quiver mutation, it looks artificial, if we consider on this triangulation picture, it is actually very natural. So if I take a mutation here, then I will get if I mutate at 1, then it will be like this, 4, 3. I just quickly did the step 1, 2, 3, and then the
arrow from 3 to 2, maybe instead of 2 to 3.
Oh, that's right. Yeah. Thank you.
No, that one's so important. Oh, you checked, right?
Okay. So, maybe this is more accurate. Yeah, that's right. Thank you. And anyway, there was a 3 cycle here and 3 cycle here, and then after mutation, we'll get another 3 cycle on the opposite side. And mutation on a triangulation will just flip the diagonal over. So it will be just simply just take the other diagonal on a given quadrilateral. So, and then still the corresponding quiver will be like this. So actually, it was quite natural on topology.
So do you have to assume the surface is orientable? In order to keep
for an ordinary quiver, yeah, it has to be orientable. Yes, oriented. But even with the non-oriented surface, there is a notion of valued quiver and mutation. But yeah, anyway, so in this context, yeah, the surface has to be orientable. Okay, so yeah, this is about quiver mutations. Okay, and then let me move on to the topic that I'm really interested in: maximal green sequences. So it will be a particular sequence of mutations. And I'm going to define this. My loose goal is to define which quivers are simpler than the others in the same mutation class. And actually, the ones that have maximal green sequences can be considered to be simple. And let Q hat be a new quiver obtained by adding. Oh, my quiver has n vertices with n. And I add another n vertices, labeled by 1 prime through n prime, and then also another arrows from n. I so this would be called, okay. I'll just give a name for this new quiver. It's called a framed quiver. And the reason that we consider this thing is partly from topology. So there is some kind of flow between vertices and triangulations, and whenever we mutate, we want to keep track of this flow, the change of flows, and then this change of flows will be captured by this frame quiver. Anyway, anyway, this comes from topology. Okay, so I'm going to introduce the maximal green sequences. Given a quiver Q, and I consider the framed quiver, so I start with Q hat, and then just mutate at so-called green vertices. Okay, then what are green vertices? I add these new vertices. But I never mutate at these things. Because this is not really a part of the original quiver, it's just there for just bookkeeping purpose. So we never mutated these new vertices, and we mutate only old vertices, but the ones that have no arrows from the new vertices. So this one is vertices. Okay, so I my first example, my first picture of quivers was looks like this. But actually, I meant this to be a framed quiver. So actually, my original quiver would be just a quiver with two vertices, and then I'll add a new set of vertices, and then to add these arrows, and then it becomes frame. Now my original quiver is a very simple one, just two vertices and a single arrow between them. And then my framed quiver looks like this. And since there is no incoming arrow from 1' or 2', any of these, by definition, this is already green. And this is also green. So, and then did I erase that? Okay, I will repeat. Now this is green. If it's not green, then let's just call it red. There is an incoming arrow from 1', so it's not green. And then add 2. And after this, we ran out of green vertices. Everything is red. And then there is nothing we can do, so we just stop. And this type of sequence is called the maximal green sequence. So precisely so in this case, this sequence 1, 2 is this is a maximal green sequence for this quiver. Is it okay? Okay, so I gave one example of a maximal green sequence, and another one is let's give a example. Was it 3? And I will start with the same quiver and the same framed quiver. So still Q is the 2 vertices quiver with 1 arrow. instead of starting mutation at 1, I'll just take a mutation at 2, then I'll get this. I'll just quickly draw the mutation sequence, and then 1, I already did this mutation in example 2 before, and finally, this is green, this is green, green, red, 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 green, and finally I get this one. So there are no more green vertices, so we stop here, and this is another maximal green sequence. So even with this very simple quiver, we have two different maximal green sequences, and but the resulting quivers are isomorphic. So after all, you will get the isomorphic quiver to the original quiver Q on the old vertices side, and the arrows are just reversed. Arrows from old new vertices are reversed. So what I just said is actually a theorem of Keller. The resulting quiver from a maximal green sequence is nice. So except for the new vertices and new arrows from new vertices, if I look at just the old part, then they are the isomorphic to the original ones. Okay, and
what do you mean by that picture?
the original quiver, if I look at just old quiver, then they are isomorphic. But if I consider this as a framed quiver, then I have an arrow from I to I prime at the beginning, but at the end I have an arrow from I prime to I.
What does it mean?
You are allowed to permute the labels of vertices. Yeah.
So you can forget the new vertices and look at the remaining, then they are isomorphic.
Yeah, that's right. Yes, right. Yeah. So already this theorem gives a feeling that it could be used to develop certain invariant. So actually, I define a certain, a very nice invariant for quiver. Quiver which has a maximal green sequence. Series is so this is a certain generating function looking like a series like this. Qn squared over 2 yn. So this is really serious. It has infinitely many terms. And quantum dilogarithm identity will look like the following. I mean, this is just one example of quantum dilogarithm identities. There are many, many identities. y1 and y2 are almost commuting variables except a factor of q. And then if we plug in these things into the dilogarithm series and then take the product, and then it turns out that these one and this one are the same. And where are they from? They are from actually the maximal green sequence. So I'm not going to give detail, but anyway, this one comes from the maximal green sequence in example 3, and this product comes from example 4. So basically, the number of mutations in a maximal green sequence will be the number of factors in this product. There are 2 mutations, 2 factors. There are 3 mutations in example 4, so I have 3 products. And there is a way to give substituting variables in here and here. It's just combinatorial data. We can read from just quiver these things. I'm not going to explain in detail, but anyways, there are certain association from a maximal green sequence to the product of a quantum dilogarithm series, and then it turns out that for all given so if we start from the same quiver and consider all possible maximal green sequences from Q, So from each maximal green sequence, there is a way to write out the product of quantum diagram series in this way, and these as a product, these things is a constant over all maximal green sequences. So this is the invariant for the quiver. I mean, this thing, this product, this Q series is the invariant. So actually, it gives lots of numerical invariants on the quiver. And Kontsevich and Soberman introduced certain fancy invariant, but it turns out that this one is actually the same as the quantum product, the logarithm product from maximal green sequences.
Wait, so if you have a sequence of mutations, then you multiply E of yi. Is that the invariant? Or?
I mean, this thing is invariant. Yeah.
What about the right hand side? What do you do? Y2 and then
Y.
What's the middle term?
Q to the negative 1/2
Yeah. So
times Y.
Why do you have that?
I didn't explain it. I mean, there is a combinatorial way of giving this expression from a maximal green sequence, but it's slightly complicated, so I don't want to talk about that now. Yeah.
Careless result maximal green sequence comes after the concept Soberman or before?
Almost the same time. Almost. No, they are not really. Almost at the same. I think Kontsevich Soberman's paper already circulated before 2008, and then I think this is around 2007. I believe that he already knew the invariance, and then. Yeah. That's right. Yeah. Yeah. His motivation was from there. Yeah. So that's a very nice result, but unfortunately, not every quiver has the maximal green sequence. So not every quiver has this fancy invariant. For the last 4 minutes, I'll introduce a result of my student. Matthew Mills. Actually, he proved the following statement, and then I simplified his proof. So. I'm going to go back to mutation finite types, quiver of mutation finite type. So the mutation class has only finitely many quivers, and then
genus bigger than or equal to what?
1, 1. This is, yeah. I mean, genus 0 surface is sphere, and sphere, to take a triangulation of sphere, we need at least 3 points. So already, I mean, yeah, actually, I don't need this condition. As soon as I say 1 point, it should be genus greater than or equal to 1. So there are only very few exceptional cases. So, and all the other quivers of mutation finite type has a maximal green sequence. And okay, and this, as I said, this quiver has only 2 quivers in the mutation class. There are very few number of quivers. Same thing here. There are, for example, genus 1. Genus 1, once punctual, the surface looks like it's just a torus. It's like this. And I have just 1 point, and then I need to take a triangulation. So there are not many triangulation on here. Something like this. So on a universal cover, it's really, it looks like I identify top and bottom and left hand, right. So these edges are labeled by the same label, and these edges are also identified. And to take a triangulation, I just take a diagonal, something like this. So essentially, up to homeomorphism, up to whatever this mapping class group, whatever, up to that thing, there are only 1. There are only 2 quivers for this surface. This one and then opposite directions. So if we have only a very few number of quivers, then we cannot do much with the maximal green sequence. So there is no such a maximal green sequence. But the hard part is to show that every other quiver has the maximal green sequence. So since I'm running out of time, and then since this produces lots of maximal green sequences, actually this gives lots of new quantum logarithm identities. And this is the end of my talk. Thank you.